All right, so hi everyone, and welcome to a new academic year of VKC Talks. My name is Amy Maley, for those of you who don't know me, and I'm a master's student at the University of British Columbia and the current host of VKC. This is actually going to be my last time hosting because I'm finishing up my master's hopefully in the next little bit. So Maya's new student Gary is going to be taking over for me. But I'll be working at SRK Consulting in Vancouver, so I'll still see lots of you guys around. Our convener, Maya Kopolova, is also here. And VKC is a series of seminars for diamond geology and related topics. And the goal is to bring academics and industry professionals together. So I'd like to acknowledge SRK Consulting, who's been a long-standing sponsor of VKC. And just a couple of housekeeping notes. Please just keep your cameras and your microphones off during the presentation to ensure a good quality of streaming. The presentation will be about 45 minutes long, after which I will help to facilitate a question and answer period. So please just keep your questions until the end. And without further ado, I would like to welcome today's speaker. So today we have Alexandrina Fulop, who's a senior petrologist at De Beers, Canada, and her areas of expertise include volcanology, sedimentology of volcanic plastic rocks, and petrology of calc-alkaline volcanics and kimberlites. Alexandrina received her PhD in geology from the University of Bucharest, focusing on volcanology and sedimentology of volcanic plastics. And she subsequently spent 15 years working in gold and base metal exploration and mining. From there, she spent 11 years at the Technical University of Cluj-Napoca at the North University of Baia Mare in Romania, where she was a lecturer and associate professor. Alexandrina has been with De Beers Canada since 2010, where she currently works as a senior petrologist. And today, Alexandrina will be speaking about her work in integrating hyperspectral imaging and XRF mapping with drill core logging. And with that, I will pass it on to you, Alexandrina, so you can share your screen here.
Yeah, it should be shared already, is it?
Not yet. You might have to reshare.
Okay. Okay.
Yeah, that's good.
Okay. So today I'm going to share some of my experience with two so-called new technologies, not that new anymore because they've been known for a while. But during the last years, these two technologies are really emerging and they have been widely used in exploration for different commodities. So we decided to test them for kimberlite core logging. We talk about hyperspectral analysis or imaging and X-ray fluorescence geochemical analysis, and also about two concepts, hyperspectral and XRF geochemical logging. From the beginning, I want to say that this is complementary to geological logging and definitely not replacing the classical geological logging as we know it. So how do we do and what these concepts mean? The spectral and the geochemical data sets, which are typically acquired with different systems with very different resolutions, acquired along the drill course, they are all converted into spectral and geochemical logs and then juxtaposed with the geological logs and the core photos. The presence of core photos and high resolution core photos is absolutely necessary because we always have to refer to something, always have to check something. Actually, the concept is proven in more than 20,000 meters of core, which has been scanned with 6 different systems, and over 4,000 geochemical measurements with different XRF analyzers, the core being from Victor, from Gachopue, and Peguachewan and Timiskaming, the last kimberlite fields discovered in De Beers. The work started in 2020 in De Beers, Canada, and is ongoing. The big advantage which we saw, and I want to start with that, is having a very large amount of data, which means having a very detailed analysis, which we could not cover with a normal 10 or 12 meter intervals sampling. Now, why using hyperspectral analysis? We all know what spectral analysis is. Hyperspectral is just acquiring much more data and identifying or mapping a suite of minerals which respond to different wavelength ranges. For the kimberlites, which are pretty much altered rock, highly altered rocks, the best response is at shortwave and visible and near infrared wavelength ranges. And that maps distinct alteration domains. So what we do, we look at these distinct alteration domains and we expect to match with a distinct geological units which we separate during geological logging, including the boundaries. Yes, we also expect to discriminate dilution based on the fact that typically dilution shows a different alteration mineralogy than the kimberlite, and we want to enjoy the large amount of data which can be processed using machine learning. Of course, there are challenges related to hyperspectral analysis, challenges related to the costs and the access to the high resolution systems. But I have to say that during the last years, actually, because there are multiple systems on the market, the price is decreased. Then other things which are related to the state of the core, the condition of the core, it has to be really clean for a good analysis. Then we have to deal with dark kimberlites and dark country rock xenoliths, which are typically aspectral. Or we have to deal with a large variety of country rock xenoliths with small sizes and sometimes interacting with the kimberlite and being replaced by complex alteration and pervasive alteration. We'll see how we deal with these kind of challenges. In the same judgment about X-ray fluorescent analysis, it's easy and cheaper and you can get faster results. Right now, there are a lot of portable XRF analyzer on the market and cheaper with better and better results and a better and better way of displaying the results in a very short time. But definitely you can do a detailed analysis because while you're logging the core, you can collect a lot of measurements in both kimberlite and country rock. And then have, again, a large amount of geochemical data that can be processed with machine learning. Big challenges because not all the elements can be analyzed because let's say the lighter elements we know they cannot be analyzed and definitely the PXRF which we have doesn't analyze sodium for example. And there is another story about the elements that interfere, and I'm talking about the rare earth elements interfering with some critical elements for the kimberlite like chromium, titanium, or nickel. So, for example, we had to configure our Vanta PXRF and decide between these elements. And of course, we choose the elements which are good for kimberlites, critical for kimberlites like chromium, titanium, and nickel. Then overall, the measured contents are typically lower than the lab results. And there is another problem, maybe even if an analysis lasts 1 minute and a half, sometimes you have to do multiple measurements on the same spot or adjacent to the same spot. Or you have to prepare the pucks, the small pucks for whole rock chemistry, which means you have to grind the kimberlite, you need a hydraulic pump, and then you need a press to prepare the pucks, and that takes a little bit more time. But if you have everything, it's possible, and you can acquire a lot of measurements. So what I'm sharing with you is our experience with two different drill cores, which were scanned with different systems for hyperspectral analysis and imaging and for geochemical analysis. And I'm going to show you the spectral logs and the geochemical logs against the geological logs. I have two examples. So drill core 1 analyzed by 4 systems, either hyperspectral analysis or hyperspectral analysis and PXRF, discrete analysis, and imaging, which is definitely more powerful, hyperspectral imaging, and another system with both hyperspectral and PXRF. It's interesting to see these systems because if they do hyperspectral analysis and also geochemical analysis, and if you can have the same data from the same spot, that's really powerful when you want to characterize the rocks. The second real core was analyzed with other two systems, one with hyperspectral imaging and another one with this time continuous X-ray fluorescent geochemical analysis, which I can tell you is extremely, extremely powerful. Everything starts with very good photos. So you have here three photos which were collected with a very high resolution camera. These are actually the best which I've seen in kimberlite so far. And we as loggers, we separated three different rock types. It was a granite kimberlite breccia and two kimberlites, two HKs, which looked slightly different, showing maybe a different alteration, but we wanted to be sure that if we lay out a sampling plan, we will not cross-cut any units or, the boundaries of potential second magma batch, and the story. So we decided to separate, and then we wanted to see how this separation is reflected in the spectral logs and the geochemical logs. And these are the first results which we got from one of our service providers. We actually bought the spectrometer from that company. We are collecting the information, the data, and they are doing the interpretation for us. It's an interesting interpretation. They do not identify single minerals, they identify mineral assemblages. And what you see here are 9 mineral assemblages which show different spectral signature. They were called spectral types or lithotypes, but in fact they are alteration mineral assemblages. Well, a combination of these mineral assemblages can be seen in GKB and other mineral assemblages or combination of mineral assemblages in K1 and K2. Now, what we see actually is the spectral map of a kimberlite, but not with the colors, with colors which were decided by the person who did the analysis for us. They don't have a value, but the legend is here. So we would know that the dominated area of saponite is at the top, and then serpentine and saponite, and at the bottom is more serpentine. So only the dominant minerals were identified, but other systems are getting to similar results. This is quite simple, but we were happy because we could recognize the different units and we could find a justification for the discrimination of the units. There is another column with hydration, but that's something related to the presence of OH, and that is sensitive for spectral analysis. I'm not getting into details. And then it's also a dilution, macro dilution. But I have to admit that dilution is not accurate because in these kind of rocks, we have a very complex country rock complex. It's all the granitoid rock from the slave craton, but in fact has different stages of alteration and definitely different signature in the spectral logs. So we accepted that it's really complicated and we tried to find a different way to discriminate dilution. Then we moved to another system which also acquired discrete hyperspectral and geochemical analysis. So the same drill core with a spectral log, and then the company who acquired the data for us offered us a platform, access to a platform where we could create the minerals. It's a long list of minerals, and then we select, of course, not all of them are in kimberlites, but we select the minerals which we found interesting for the kimberlite, and also looking at the minerals which can actually discriminate the units. And they are not a lot. We found only the smectite total, looking slightly different, with much more in the breccia than in the kimberlite. We can see the magnesium smectite, which is restricted to the granite breccia. We look at the carbonate, especially the dolomite, which is in the kimberlite and the calcite, but that's only to separate the granite from the kimberlite, which is actually quite easy to do it. We also did the chemistry. This is PXRF, 15, 20 centimeters distance between the measurements. And what we notice is what we actually expected, that the elements which are in the kimberlite are definitely in higher abundance in the kimberlite, and the elements which are typical in the granite are much higher in the country rock. But we can also see the peaks with a lot of peaks which are related to the country rock xenoliths from the breccia. What we notice is the presence of this manganese much higher in K1 than K2, another justification for the separation of the two units, even if maybe later these units will be lumped together after we find out where that manganese sits, if it's related to some kind of alteration, because there were other situations where we found manganese in an altered country rock and the interaction with the kimberlite. But in this case, we are happy with the separation which we made based, if you want, confirmed by the information which we got from hyperspectral and geochemical data. Now we move to more sophisticated systems, hyperspectral imaging, which means acquiring a lot of images, hyperspectral images. We could say that it's discrete, but actually it's not discrete because it's contiguous, so measurement after measurement with thousands of analyses, and everything is combined in something which is unique, and it's offered only by this company, the mineral class map. So they compiled actually all the spectra identifying the minerals they were able to identify, and they put them in a map. It's the first and the only company I've seen with such a map. Here is the legend. It shows the minerals which are in the kimberlite and the minerals in the granite. And you can see in the granite the white mica and chloride, probably not separated. The chloride, this aspectral means there is another mineral there, but couldn't be identified because it was aspectral. The carbonate is in the granite. And then you can see the kimberlite and JKB, which is dominated by the saponite, different types of saponite identified based on different spectral parameters, and the serpentine, which is dominant in K1 and K2, probably different varieties of serpentine because they are with different colors. And you can see here there is a serpentine, another serpentine, a serpentine type 2, and so multiple types of serpentine. So the system has such high resolution and the data are so finely tuned that they can identify with the spectra different types of the same mineral. And then they offered us plenty of logs of minerals, but we selected what was important for us, and we selected the saponite. And you can see different varieties of saponite based on differences in color and different types of serpentine. And then we selected the white mica for the granite just because we wanted something which separates completely the granite from the kimberlite. It's an example. As I said, we can generate multiple logs or maps like this, and they also have a different way of providing the data, like this one. These are the so-called numerical logs, where you can get the log of a saponite, of a serpentine, a different type of serpentine, and even an unknown clay and serpentine mix because of the mixtures of minerals not all being identified. And then we get the percentage of each of the minerals in the rock. So tabular data with amount of minerals. Then with the same system, we look at dilution, and then we saw dilution really well expressed in the mineral class map, in the saponite log, showing that there is saponite in the kimberlite, but there is also saponite on the granite. We see the map of vermiculite, which stays in the kimberlite as an alteration mineral. Then even the halo of the granite, the serpentine, is beautifully displayed, and some iron oxides. But if you want to look at dilution everywhere, to see everywhere the fresh granite, you won't find exactly the same spectral signature. They might find a very different alteration, and it's difficult to say and identify all the granite and then quantify it. Another example actually confirms what I'm saying, that you can see a partially altered granite or highly altered granite, and in the spectral map, it looks like slightly fresh granite in the center, but you don't really see, or you see a saponite replacing some of the granite, but that saponite actually merges with the saponite from the kimberlite. And same here, when some small clasts are really altered, you don't see them, so you cannot estimate dilution. That's really worth trying something else to identify, but maybe it's also related to the complexity of the kimberlite, which is not really appropriate for this kind of estimation. It is interesting because they also can separate, apparently they can separate the saponite, which is on an altered granite, from the saponite, which is on an altered kimberlite, but or even they can separate the serpentine on olivine from the serpentine on the kimberlite, but we didn't see that in this example which we had. The same drill core was analyzed, in this time in-house with a PXRF, with our PXRF. I measured, there were 1400 measurements, and then I asked our data scientists to do some plots that can be done really easily and see the differences between the different units, and he did this unsupervised machine learning, and that's what we got. Definitely different amounts of nickel, chromium, niobium in the kimberlite and the granite. I want to show you that, I hope you notice that the core is here horizontal and here is vertical. So GKB and K1 and then K2. Very small differences between the units, and quite large range of analysis, but that's the PXRF. And I think that's compensated by the large amount of data, which shows us exactly what the trends are. But then we see the same, that manganese is much higher here, and that means our PXRF is compatible with the other PXRF which analyzed previously with the previous system. Another system, so this is the most complex with the highest resolution, and it's hyperspectral imaging, but we did not get a very specific map, but we were led to generate our own maps based on features, specific spectral features, depths of absorption in this case. We already know what to do because we are used with these spectral features from the previous test. So I tried to select, there were like eight features, and I selected what was useful from the perspective of separating the different units and seeing dilution. And these three maps were the best. We don't know the minerals. Of course, we can imagine they are the same minerals, the saponite and the serpentine here, but we see the differences, and that's what we want to see. And of course, the difference with the granite. Here we see dilution, but it's mostly fresh granite dilution. Here we will see, and we will see in the next slide, it's not only the kimberlite, but it's also dilution and an altered dilution, which was not visible in the other maps. Our data scientists also looked at and did some unsupervised machine learning analysis on the geochemical data acquired with the same system. And again, there are thousands of analyses here. And his observation was that what is granite here and is granite here can be recognized as granite here in the country rock, in the kimberlite. And actually, this is a kind of a global dilution. We cannot allocate to a certain place and to a certain row, but we get the information about how much dilution is. And that was quite spectacular, actually, to to have a dilution, a global dilution based on the geochemistry data. And we look at dilution in the same system, acquired with the same system, as you saw before. This is the fresh granite, and here are different maps with different colors, but with altered granite, and here again with altered granite. And this is the best because some of the highly altered granite clasts are visible here. I haven't checked with all of them, but definitely most of them are visible. So this is probably the most powerful map which could be used to identify the altered granites, and this one for the fresh granites. But the big problem is we need, if we want to estimate dilution, we need to use different maps. We can't see all dilution in one map. More than that, another unsupervised machine learning, which was carried out by Navid, by our data scientists, shows this time exactly the location of dilution. So this is every single row of the drill core with a dilution. So this is really, really powerful and might simplify a lot of work in exploration, but we need to do more tests, and definitely the work is still in progress. Now, talking a little bit more about unsupervised machine learning solutions, Navid looked at all the spectral data which we had from the very different systems, and he started processing the data in different ways and getting to some conclusions. For example, he looked at the first system, which was that one which is performing discrete analyses, and then he clustered the spectra which show affinities, meaning similar shapes. And actually, he did that using a global wavelength range. This is all shortwave from 1350 to 2410 nanometers. And then he noticed that, yes, he can do some work. He can discriminate a few spectra which can be interpreted as some minerals, but he did not see dilution. Then he restricted the band to 2300 nanometers, and then he started noticing dilution and actually matching with what it is in the core. It's work in progress. We didn't go on. We try only to prove the concept, and then the work stopped from this. It was a lot of work to decide how many clusters, how far can we go with the interpretation. A lot of work which was done by Navid. And then he used the other system with the highest amount of data, the largest volume of spectral data, and did the same global evaluation, and it didn't show exactly what we expected. I mean, actually, we expected not to have the best results, but we had to test. And then also band restricted to 1400s, 22, 20, 2300s, and the other one. And you can easily see the differences between the units. And what is interesting, you don't see a lot of difference between the granite and the granite breccia, but in fact it depends on how much is granite and how much is kimberlite. I did not fully understand, but probably some of the minerals which are in the granite are also in the kimberlite. It's not clear for me, but what is clear that the granite breccia and K1 and K2 were definitely discriminated. So these are some tests. It's work in progress. I think he's going to do more work. We test different absorption depths. That's what they are. We already know what the absorption depths for saponite and what it is for the serpentine and for the other minerals in kimberlite. But it's a lot of overlap, and these kimberlites, which we thought they were simple to be analyzed, are actually very complex and full of mixtures of minerals. Another way of looking at the spectral data, Navid's idea was same band restricted and the same amount of very large amount of spectral data, But all the images were created by him, not by the system. He only looked at the data and processed them. And then he started with the entire spectral shortwave infrared range, and started with 1208, and he added 50 nanometers, and then he created all these maps. That was, let's find a map which shows dilution. And we got to 20 to 50 nanometers, where we were able to see dilution. And then there is a color chart, and then you can mask. You're gonna see only what is red, or you're gonna see only what is yellow, depending on what you want. Again, it's work in progress. We don't have a final resolution, but we see that it's possible to do it. Eventually, the most complex work he did on actually on the very simple results, high resolution RGB photos. So we saw that it is complex. Every kimberlite is different, and then we have to do the work and adjust everything to the spectral images and geochemistry for every single kimberlite. And we thought of finding something which is easier, and he looked at the high resolution RGB photos, and he used deep learning to do the segmentation of dilution. So what you see here actually is the proof of concept, shows that every single piece, no matter what it is, can be segmented and a different color is allocated to it. And then you decide, this is the kimberlite, this is the granite class, and I want to see it. And then you mask all the others. And that's what you see here. One type of dilution and all the others masked. And then you can easily estimate dilution based on that. But that's one type of dilution. You can have 2, 3, 4 types of dilution, and you will repeat the exercise for every single class, and then you get a final dilution. I think this is actually the most complex. It's been the most challenging for him, for what he used, and if it works, it's going to be the easiest. And a second real core, which was analyzed only with two systems, but the complex systems, continuous hyperspectral imaging, and this time continuous geochemical analysis, XRF geochemical analysis. The rocks are relatively similar. They are HKs and granite kimberlite breccias. Small differences. We separated 4 units, and they are like, this is fresher, this is slightly older, more alteration, and more alteration in the kimberlite, and then less alteration in the granite. And so once again, it's important to have good photos. And then hyperspectral imaging, opposite to the first service provider, which gave us final products, gave us mineral maps, gave us mineral logs. This one gave us the opportunity to select our own maps. They have a very nice and easy platform to use, and they have a long selection of absorption depths or features, spectral features, and then you select what you want and you try until you find the map which you want. The simplest map, so we have 4 units here, and the simplest map which can be created doesn't show the units, but it shows the dominant minerals. This is the gray is the serpentine, and the blue is the saponite. So these two different areas show 2 different minerals as dominant. And with these kind of maps, all you can see is actually the fresh granite, and that's all. You don't see dilution. Then we started using, after we look at this map, we look at the report about these kind of maps, and then we get the percentage of the minerals. So this is the serpentine, and then we will see here, we'll get a table with the percentage of the serpentine, and these minerals are unclassified, and this is saponite with a little bit of serpentine, and with a little bit of elite, which was the only one identified on the granite, on the feldspar of the granite. So a second map, we generated it. As I said, we can have multiple, but I like this one because this one shows our units. And this is depth of absorption 250, which you already know from the previous systems, and shows us also dilution, not only the different units. Besides that, they use a lot of artificial intelligence in creating the maps, and they offered us so-called self-organizing maps. And these are two different self-organizing maps, which also show the different units, but unfortunately, the minerals are not labeled. But what we see here in the two reports of the same maps, we see there were 20 classes of minerals. That means there were a lot of minerals with very subtle differences which couldn't be differentiated, but they exist. And they give us the percentages, and we can also see the units in these, not as well as in 2 to 50, but I will show you a little bit later that actually dilution can be well seen in these kind of maps. So I like the fact that we had the tool. We decided what we use, and we decided how happy we are with each map and which one is the best. We look at dilution in these hyperspectral images, and we see the fresh granite nicely in red here, in red here, in red here, pretty much in shortwave D2250, the same in one of the self-organizing maps, but I also wanted to see the altered granite, and there is a little bit of altered granite here and here, and here with green. First observation, is it a different country rock or it's a different granite? I don't know, but what I know is that we cannot just simply say count whatever is green or count whatever is red to estimate dilution, because we have red and green everywhere, showing an overlap of different mineral assemblages, showing the red is also on joints, and the red is also at the margins of the core, which is kind of a effect of curvature probably. But I like very much the maps for the separation of the units, and I'm pretty sure that in a way we will be able to estimate dilution in this, just to be patient and generate multiple maps, decide how many types of country rock we have, or what kind of differences are between them, and decide about multiple maps and estimate. I like very much the self-organizing map, and this is more like for us as petrologists. Look at the beautiful granite and the beautiful halo around the granite, but that's one of the self-organizing maps which doesn't classify the minerals. But I can tell you that this is actually a saponite. Um, the last example is with continuous XRF geochemical data, and this is a very interesting machine which we tested in 2020, and that's in one drill core around 1500 XRF analysis, and this time we had um, geochemical analysis from ACME, and we could test against those geochemical analyses, and we see that the trends are identical. But we also notice that all the values are lower than the values obtained in the lab. It's the same as previously. It's more like dilution, which is noticed. Um, Definitely K1 with more nickel, and the others decreasing in nickel based on dilution. The same about chromium, the same about niobium, and then silica is showing how increases in as dilution increases. That's pretty simple. It's more like testing it and seeing if we really have multiple units or not. And then another diagram using the same unsupervised machine learning, showing differences, not that much, just slightly different ratios between the different groups of elements, and probably the last two granite breccias almost similar. But that's not important. It's important that we can find different way of looking at the data, and especially when you have a lot of data. So conclusions. Once again, I want to reiterate that hyperspectral and geochemical logging are not replacing geological logging. It's impossible to cover the complexity of geological logging only with hyperspectral and geochemical, but they offer us a lot of good data which we can use, and we can learn a little bit of mineral chemistry and learn a little bit of spectral geology to understand more. The big advantage definitely is in the large volume of data and the processing using machine learning solutions. The same idea: identify domains of alteration, domains with consistent geochemistry, and expect to correspond to geological units. Question is, what do we do when they mismatch? And definitely the mismatch must be investigated, and I experienced myself that. So what am I doing? Am I going to change the log based on the geological, or based on the geochemical or the spectral, or not? Eventually, the decision was I will look for more geological evidence. I won't change anything unless I can support that change with the geological observations. But yeah, so I'm seeing it as increasing the confidence in geological logging, because if you see a huge mismatch, definitely you have to go back and look at the geological log. We say that these are objective data, and I do believe they are objective data. More or less, it depends on who's doing data interpretation, but based on my experience, all the spectral geologists are fantastic, but the systems are different. Higher resolution, lower resolution. The higher the resolution, the better. Then I can conclude that dilution can be quantified on spectral and geochemical datasets, might be a little bit more complicated, and pretty much depending on how complex the kimberlite and the country rock are. But RGB photos are really useful, and that's probably the way forward. As I said, the work is in progress, but the concept is proven. What is interesting, based on my observations after looking at 20,000 meters of spectral logs, and not that many geochemical logs, but spectral logs, I noticed that they tend to simplify the geology. So I have to go back and check. I can give you an example. In one of the pipes, we used to, it was so complicated that we had to separate a lot of zones. We wanted to see what's happening, and it was difficult to lump the zones into units because there were too many. Eventually, we had 3 units. When I look at the spectral logs, first of all, I saw how well the zones were because they were matching with different mineral assemblages. But overall, they were the same mineral assemblages with differences in the percentage. And eventually, I realized that we can give up using zones, and we have only two units. It was quite a discovery, to be honest. Yeah, it's good to work in detail and get a lot of details, but sometimes it's also good to simplify, especially if that pipe is gonna go through the pipeline and it's gonna be mined at some point. It's important to simplify. It's important to see the different units, and it doesn't matter if the alteration minerals are classified or not. It's important to see the differences. As I said at the beginning, there are challenges, disadvantages related to the complexity of the kimberlite and of the country rock, on their interaction, of the mixtures of minerals, the pervasive alteration. When it's pervasive alteration, it's quite difficult, but normally you should be able to identify different type of that mineral if one, like saponite, replaces the granite, or saponite replaces the olivine. That should be a different type of saponite. And of course, another challenge and the problem of dark rocks, and which are aspectral. Once again, the limitations depend on the wavelength range, depend on the resolution of the acquired data, and the resolution of the photos. Definitely, hyperspectral imaging and continuous XRF analysis are better. For example, with the XRF analysis, the way that system was, we were able to plot on top of the core all the chemistry. Every 10 centimeters or every meter averages of the chemistry was on top of the core, so we could see immediately where that element comes from. It comes from the country rock, it belongs to the kimberlite. It offered a totally different perspective. So I like this system, but once again, we cannot cover the complexity of our geological logging with hyperspectral and geochemical, but it helps us a lot. Thank you so much. If you have questions, I'm here to answer.
Thank you very much, Alexandrina. That was a great talk. If anyone has any questions, you can either ask directly or send it to me or send it to everyone in the chat, and I can ask for you. I'm going to start off with a quick question, if you don't mind. I know in the examples that you showed, like they did have some gradational boundaries between the units, right? But if you had maybe an RVK that was very gradational, and you had a cutoff of you needed, 50% catalytic material for it to be economic. How do you think this would deal with that?
What do you mean with half? It's economic. You mean it's ore, it's kimberlite, and the rest is country rock, right?
Yeah.
Do you deal? Well, you would definitely in a spectral log, you will definitely see a boundary between what is kimberlite and what is country rock. You will definitely see it. I mean, you're seeing units. So you're not only seeing a country rock, or it depends on the map actually. But it was an interesting experience with the boundaries, because sometimes what I saw that was a gradational boundary was because of alteration. I couldn't see it well. It was actually a sharp boundary. And sometimes with a spectral log, you can have a very reliable boundary. Yeah. So yeah, it has to be it has to be an example to judge it. This is for example, I lumped some units based on the spectral data, because I was not sure on the boundary. I was like, it's here, it's there. In fact, there was no boundary. So it's we have to see examples to be able to decide.
Thanks.
Thank you, Alexandrina. I have a question about hyperspectral imaging. So when you talk about the mineral classification, I realized you didn't mention about some like diamond indicated mineral, for example, garnet, ilmenite, or chromite, which are important in exploration. Probably because opaque mineral are hard to be detected by hyperspectral. And when you evaluate the result or do the core logging, how do you take this into account?
Yes, so all the systems which I showed you stay with shortwave infrared and visible and near infrared, but actually the last system with the last example also has the long wave infrared. And that's good to identify the fresh minerals like the fresh olivine and the fresh garnet, for example, or CPX. But it's so rare that you have all of it fresh in the kimberlite. Yes, if you have all of it fresh, then it's worth using long wave, which is more expensive than the others. And maybe you can count I know that the guys are actually working on that, try to quantify the abundance of garnet, for example, or the abundance of olivine. But when I look at the maps, half of the olivine was altered, and they were not able to identify it with long wave. So that is a problem. Maybe if you combine if you have different wavelength ranges in one system, you can combine the different maps, but that's going to be more expensive at this stage. Even if the prices are decreasing, it's still expensive.
Thank you.
Another question that I had is, how much time does it take? Like, how much extra time does it take to do these over top of just logging core?
Yes. So we did the logging as usual, and then actually before doing the logging, we cleaned the core as usual, and then we measured with our system. I'm talking about our system. For the other systems which are more complex, you have to ship the core. There are not a lot of machines across the globe, and then you sometimes you have to be on a queue and wait for your turn. So that's what I said, that it's challenging to have access to a high resolution system. But at PDAC this year, I realized there are more and more systems, and there are several in Canada which are really good. And with our system, it takes about a week. We collect the information, we send it to the service provider, and then he's sending us back the different lithotypes or spectral or mineral assemblages, and that stack image with all the combination of mineral. It's about a week. Yeah, we can improve the time, but the week is still good.
Yeah. Does anyone else have anything they'd like to ask?
Yes. So to put it into context, when I logged core for decades, I would log 200 or 300 meters a day and very seldom go back to the core once you were fully trained. So the time difference is huge. But just to clarify from the previous question too, I mean, the order of importance of what I put on what you need to identify units or ideally phases of kimberlite is number one, the indicator minerals, which really you can't pick up. Then you also said the olivine size, macrocrystal size and abundance, you can't really pick up. And then that's the first thing, the mantle minerals. The second thing are the primary minerals. So in all of those things you showed, there was monticelite mentioned once, but it doesn't pick up the ground mass minerals.
Yes,
and then primary versus secondary, it didn't really distinguish between primary and secondary, or I just find it difficult to see how it increases the confidence hugely of the units, so enough to warrant all the money and time that you're talking about. So I'm not completely convinced yet. So primary versus secondary, such as serpentine and carbonate, because there was carbonate in some of the units and not in the others. And then the fourth thing is textures. So clearly, or maybe I shouldn't say, but those rocks came from Gachaque and they were transitional textures, KPK, KPKT, HKT, HK. And the features were clear, and if they were one phase of kimberlite, they should have gradational boundaries. So then there was country rock dilution, which is a whole nother thing.
Yes.
So what is your opinion in warranting all this extra work to log a core?
Well, I think even if the data are with a low resolution, they still reflect the units, and that's giving me a peace of mind, I would say. So if you have these complex rocks, I mean, Gachaque is really complex, and it's a lot of alteration, and the boundaries between the units are actually gradational, and I didn't see a single sharp unit, a sharp boundary between them, and sometimes you see changes. Sometimes it's from one, let's use the term, from TK to TKT and back to TK. And somehow the alteration shows me that a lot of the features are actually related to alteration and the interaction with the granite. That's what I'm seeing. And actually, Casey described it perfectly in his paper. Perfect. And I saw that with my eyes. But I still believe that what we get from these spectral images and from geochemistry gives us more confidence. It's not.
A lot of what you're describing there is actually the interaction between the kimberlite. It's not secondary and post alteration. It's most of that stuff at Cachique is inside the magmatic system, right? So it's all part of the rocks becoming KPKs as they're in place, right?
Yes, true. Yeah, and about identifying texture. Of course, you cannot see the texture in the spectral log. You would look at the photos. A lot of things cannot be seen with a spectral image. But my experience, when we did Pegueche, for example, it was not economic, and it was so difficult to log the core because it was all a dark kimberlite with tiny, tiny indicator minerals, almost invisible, and olivine almost invisible. We had no idea. We look at textures, we look at the different relationships at country rock, and was a large variety of country rock, was really difficult. And then we worked with zones. And when I actually saw the logs, there were two different units and so well separated by the different mineral assemblages, about metasomatism, alteration minerals. Look, it's only a tool, it's not replacing.
Yeah.
Definitely, it's only a tool. And I think it's worth the work because, I think that for the future, even the olivine, if they can see now an olivine, a serpentine on an olivine, which is different than the serpentine in the ground mass, for example, it's still an improvement. Or
But the big problem in a place like Cachique, I mean, I could identify the textures just on the screen here,
yes.
Is that the replacement of the olivine changes. It can even change within the zone around the xenolith, etc. Right? So those are all primary features throughout. And I don't know how a machine can actually pick up that wide variation to identify all the olivines or even all the xenoliths or something, because it's a continuous and oscillating system, which is outstandingly displayed at Cachique.
Yeah, it is. It is. But once again, we do our job, but we also do this one. And, if we can do dilution, actually is a major achievement. That is actually my top priority, to do dilution and stop counting, because it's 21st century.
I measured that. Anyway, yeah, all right. Because even in dilution, in a place like Cachique, where you go through those textures, it was one photograph, one screen, one of your slides showed the change in the xenolith beautifully, right? From dark xenolith to green in the HKT to whatever and whatever, and then can the machine actually pick up those oscillations and then put divisions between them?
Yes,
I would think that was quite hard, but you can prove me wrong one day.
No, you are right. But you know what it is actually what I noticed about TKT and TK. Actually, it's a lot of granite which is not accounted for because some of the green material, it's not kimberlite. And that I noticed.
Well, if you go back to your photograph, it showed spectacularly. It's not granite, but it is dilution. It is the granite dilution that's been replaced by serpentine from external fluids.
Yes,
you had a spectacular photograph.
Saponite. I noticed every time it's a lot of granite, it's actually a lot of saponite. And I tested another technology. I'm not talking now about it, but I think it's absolutely spectacular because it scans the thin sections and identifies the minerals based on chemistry. It's a Zeiss machine. The work is done in Canada. And this is how I saw that you need a lot of granite to turn into saponite. Otherwise, it's serpentine. And I could see the saponite around the granite clast and then the serpentine in the ground mass. Spectacular things with chemistry. But again, it depends on the resolution. For example, if there is a phlogopite, the phlogopite, it's not perfectly outlined, but it comes in the chemistry of the minerals because they give us a table with the minerals. It's not a moment, but there are spectacular technologies out there which help us to understand even the texture in TK, for example. Even the texture, it's beautiful in thin section in the iOS system. And you don't see a lot in a thin section. You see some brown smectite and maybe some fresh granite, and in between here and there an olivine and some ground mass spinel, not a lot, which shows that there is a lot of granite. I started thinking of the granite that what we do in terms of dilution is not correct because there is a lot of granite out there which can be accounted for, cannot be measured. But that's based on my experience, and that's old gachokuya. I didn't see anything of the new gachokuya, but in the old stuff, that's what I saw. I recommend iOS and the Zeiss machine, just to calibrate sometimes a type of kimberlite. One thin section, not more. It's pretty expensive. Yeah.
Thank you.
Can I continue with several questions about saponite and smectite?
Yes.
So you showed all these spectacular maps that show distribution of these minerals, but how do we know that these are indeed correct mineralogical names? And is that something that you assigned based on the chemistry you've seen, or is it some relative name that the machine assigned, and then we don't know if that is indeed that type of sheet hydrosilicate or something else that could be with the same peaks, but not necessarily with the same composition?
Yeah. So Maya, yes, that's the same principle of spectral analysis, something that we've been doing like many years ago. It's the same principle here. They have some spectral parameters and is a spectral geologist who identifies the minerals. And that, I agree, depends on his experience and depends on what kind of spectral library. But I saw one of the companies, they are really, really good in that. So if they can identify multiple types of serpentine or multiple types of smectite or saponite, and they can see actually how the composition is changing from a magnesium smectite to an iron smectite. So he can find that. I think it's all based on the library they have, and this is not a machine which identifies. But yes, they use some AI to do maybe probably the compilation in a spectral map because they have multidimensional spectra. It's not easy to understand for us, but maybe that one is using machine learning and the maps which probably match the different spectra. Same as we try to do and cluster the spectra which show affinities. But other than that, it's their interpretation. It's not an interpretation of a machine. And probably it started with a lot of spectral analysis, like point analysis, trying to understand. But don't forget, all the libraries are made of analyses which come from pure material, and we rarely have pure material in the kimberlite. It's more like a mixture. So I expect to see changes between different varieties. I trust all the systems. I trust the saponite is saponite and the serpentine is serpentine. What I don't understand sometimes, what kind of type and so on, but for me it's enough at this stage if I understand about approximately the composition of the rock. It doesn't mean I'm not doing microscopy or logging the core, but I add something new. And I studied a lot how the saponite is formed, and I realized you need the granite to have the saponite form, and it's not that the serpentine turns into saponite, it's a complex. It needs aluminum from the granite, and it's really complex. I look at other rocks, not kimberlites, trying to understand. I didn't finish my study, but it's interesting to see in a kimberlite that you have the granite and the halo, which is actually the kimberlite assimilating the granite, becomes saponite. And the rest, when there is no granite, is serpentine. And I saw that in the last system, I saw that in many places. And it's not accessible right now to me, but would be nice to test with a PXRF and see exactly the chemical composition. Even if it's XRF, it's still geochemical composition.
Yeah, can I continue with one more question?
Yes.
This time about the general state of things when we're looking at hyperspectral imaging in kimberlites. I understand, or maybe I presume, that it's more difficult to do these things for kimberlite if we think about metal exploration and logging core there and using hyperspectral there. That should be so much easier because the contrast in all the properties would be absolutely amazing if we're looking for sulfides in quartz, yeah? And here we're hardly pressed to distinguish between serpentine and smectite, whereas in metal exploration, everything is probably easier and cheaper and more advanced and more traditional these days. Is it right?
Yes, it's right, Maya. It's much easier to identify a vein which has a few minerals. Well, sometimes there are mixtures that it's not that easy, but it's much easier than in a kimberlite. But still, we get these very good results. I mean, we can identify the units and eventually we can identify dilution. And myself, I'm extremely happy with the system which we have. We don't need a very sophisticated system actually to see the differences. It's quick and it gives you another layer of information, another layer of confidence, I would say. And yeah, I do believe that on a long term, at some point in the mining phase, maybe you can only do spectral analysis because you don't need to have thin sections and everything from every single drill core when you already know your kimberlite and your pipe. But yeah, we'll see in the future. It's ongoing work. I don't have a final resolution. As I said, I had very different results and sometimes with high confidence, sometimes with less confidence, but they were objective conditions. Like having a dark kimberlite or having a dark country rock, that's it, is aspectral. You cannot blame anyone.
Thank you.
Okay, so Michelle just wrote something in the chat, kind of going back to looking at, the difference, whether we can pull out the difference between saponite and serpentine. And you just kind of added a point that it is fairly simple. If they're mixed, which they usually are, things can get a bit more complicated, but because it's a chemical change, as long as there is that chemical change, the spectra will change as well.
Yeah.
And then Martin left just kind of a brief comment in here. Do you want to comment on what you wrote there, Martin?
Hi, everybody. Yeah, Alexandrina, hi, long time no see, and thank you for a really great, interesting talk. I've just got a helicopter views. I'm not a petrologist. I'm not an AI expert at all, but the questions that I see happening that you mentioned unsupervised deep learning, and one of the AI large language models aspects is, have you asked the right questions? Then my other comments are, how relevant is the application to exploration versus mining and evaluation? And the computing power needs and the costs and the turnaround time. And for example, you mentioned you was talk about the serpentinized granite and being able to recognize replacement processes. But is that serpentinized granite mineralized, and is that relevant to a mining model if that unit? Well, it would be relevant if that unit's not mineralized. So can you kind of differentiate those things?
Okay, so yeah, that's complex. First of all, you used deep unsupervised machine learning, and that's these are two different things. Unsupervised is something really easy, and then there is a training, and it's going to be a supervised machine learning. A deep learning is something really deep, and yeah, so they are different. And look, I do believe that. Okay, I don't know exactly how to phrase the second question. I think it's worse because once you have alteration model. That's what you get. Let's think of Gachokuye. We get an alteration model, but we already sampled and we already know where is the ore. And we also have an idea about where is more dilution and where is more ore or less ore. And maybe with an alteration model, we can decide, because that alteration model is going to help also in the plant. It's going to be important if it's serpentine or saponite. So it's just my vision. It doesn't mean I'm right. But maybe for the future, when we know we already have 100 drill cores, which was logged and sampled, and we have an idea about the ore, and we have LDDs. And by the way, with LDDs, you can log, do spectral logging and geochemical logging. Right now, I have a project like that, and I'm working on Victor rocks. And if we can separate the Victor rocks with spectral analysis and PXRF, we are the best, because these are really difficult to be discriminated. So I see a lot of application in the mining with hyperspectral. And I see a moment when everything becomes really simple. And yeah, but I do hope that we still do geological logging. But sometimes if we look at the photos and we look at the spectral logs, maybe it's going to send us to do more geology, or maybe it's going to say, no, it's the same unit and let's go on and mine it. It's a vision, good or bad.
Thank you, Alexandrina.
Yes, no problem.
Hi.
Go ahead.
Do you hear me?
Yep.
Hi. Thank you. Very interesting talk. Fascinating stuff. I'm not a geologist, so excuse my ignorance. I have a couple of questions. First, you mentioned a company that give you the option to choose how to map the units or something like that.
Yes. Can I answer now?
So my question is, so they provide you with the spectra and you decide which spectra match to which unit, and the other part isn't that risky in terms of confirmation bias?
Okay, so I'm sorry, that means I was not explicit enough. It's not us who decides what the minerals are. It's us, we decide which map we use. So all this map, all this data exists already. The interpretation was done by the spectral geologist, and we only select the map which we want, depending on the spectral features, spectral parameters, call them as you want, and we decide. Of course, the easiest is to get everything done, but sometimes it's good also to think about and select. And especially if you have different type of dilution, then you have to select different types of maps to see the entire variety of dilution. So it's good to do the job yourself. But once again, the interpretation is there. It's not you. It's a spectral geologist who's doing the interpretation.
So they're providing multiple maps and you pick what makes more geological sense. Okay, thank you. Another questions, sorry for bugging you, taking the time. Near the end, you mentioned something about the zones versus unit perspective. I'm not sure I understand that. So if you could clarify it with few sentences.
Yeah, so sometimes we have, in the beers at least, that's the only experience I have in kimberlites, we have this zonal approach. When we are not sure about the units from the beginning, we used to have subdivisions, which are called zones, and then we combine the zones into a unit. So this is zonation. And then the spectral log actually showed me that each zone was slightly different in terms of alteration, but it was not worse to separate all of them, because we could just ignore and do the unit separation, but we were not sure. So I think I have a lot of experience in core logging, but sometimes you can have really difficult rocks. And I think it's better to start with a lot of details. But adding the spectral log, it's going to help you to simplify. Let's say it's going to give another layer of confidence.
Okay, just to make sure I understand correctly. So zones here means sort of subunit. It doesn't mean okay.
Yes,
Oh, thank you.
yes, subdivisions, yes.
Thank you very much.
Does anyone else have anything that they'd like to ask before we wrap up? No, doesn't look like it. Okay, I'm gonna stop the recording here then.